Hi, this is Tim Malloy with video 4-1 on Faraday's law and Lenz's law. I'm going to be doing problem number 9, and the pointer's not working, so I'll choose a pen. Okay, so a piece of insulated wire is shaped into a figure 8 as shown in the figure below. For simplicity, model the two halves of the figure 8 as circles. It's cut off. The radius of the upper circle is 4 centimeters, and that of the lower circle is 7 centimeters. Wire has a uniform resistance per unit length of 2 ohms per meter. A uniform magnetic field is applied perpendicular to the plane of the two circles in the direction shown. Magnetic field is increasing at a constant rate of 1.8 teslas per second. We need to find the magnitude of the induced current in the wire, as well as the direction. So first off, we got Lenz's law here, which says when there's a change in the magnetic flux. So usually, magnetic flux involves area and magnetic field. So when one of those changes, in this case, it's the magnetic field. The polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change in the magnetic flux. So let's say I have a field going inwards, and it's increasing. Then we're going to have a field out of the page. And if I have a field inwards that's decreasing, well, actually, we're going to flip that around, and it's also still going to be into the page. That's really it, and it's kind of about how you apply it where anything gets tricky. Oh, okay, my explanation disappeared. Oh well. Okay, so let's do part B first. So recall Lenz's law like I just taught. So since this field is into the page and out of the page field would oppose that, and B is increasing, so no need to flip the field. Yes, okay. So this is a little complicated, just hang tight. I zoomed in, so hopefully not overwhelming. So again, we got at the top we've got the opposing field out of the page, so then that would mean a counterclockwise rotation. And interestingly, it's the same thing with the bottom ring. So now I'm going to show you what the net charge flow looks like. So recall how there's greater flux because the area is greater in this bottom ring. So the induced current is greater in the bottom. So what that means is that this blue current is going to overpower this red current, and we're going to get something that looks like this, where we still have the counterclockwise in the bottom, but then that kind of overpowers this top current to continue on the path. So then we have a clockwise top, or yes, we have a clockwise top, and then that's the trick. That the top is clockwise because the bottom overpowers it because the magnetic flux is greater. So we'll go ahead and check that. Okay, clockwise in the upper loop, counterclockwise in the lower loop. I think that's what I put. Wait a minute. Okay, it is perfect. Okay, and then question A asks, find the magnitude of the induced current in the wire. Uh-oh. Okay. So question is a little packed. I'm thinking, okay, how are we going to get there? So what do we know? Let's do that R over L calculation really easy. We know that it'll be equal to resistance over the length of the loop. Length of the loop, well, the loop is 2 circles, so it's just this circumference of the top and the circumference of the bottom. So there we go. I plugged in known value for R over L. We don't know R. We do know the radius, or the length of this loop rather. Multiply by this denominator, and we get resistance equals 1.38 ohms. So we know V equals IR. This is what's his name? Is it no, not Ampere's law. Ohm's law. This is Ohm's law. Yes. And then so we have this R. We could get this V using Faraday's law, which I decided to do. So one loop, so our n is going to be 1. Area is constant, so it'll be dB dt times A. And then recall that I said the flux currents oppose each other. So we're gonna hop over here again. Pulled the A out of this rate. Yeah, okay. And then we have what we have here is because we know BA equals magnetic flux, right? So this is really magnetic flux of the bottom, right? Because we're gonna distributive property. The area is gonna be multiplied by the field. So it's that bottom flux, the bottom flux, which is greater than the top flux minus the top flux. Hmm. So the math makes sense. It does once you multiply everything out. You just got to make sure you catch the subtraction part and you don't add them. I think you would add them if maybe this was like, going in a perfect figure eight, but it isn't. So you have to subtract. So then we plug in our value. Again, this is area magnetic field. I already said that. And then the negative sign doesn't really matter in this equation. It just kind of says, hey, make sure you oppose the changing field, right? Mhm. It's more of a conceptual thing. And I only kind of started to get that because you just throw the negative sign in the formula, but I only really started to understand that once I was doing the problems and it made sense. Okay, so now we have our voltage or EMF, and we also have our resistance. So we can put one over the other, and we can get a current of 0.0135 amps. Put that in the website, and it's all good. So that's that problem completed. So my takeaways is you got to know Lenz's law very well. I missed the class practice, so I had to do some extra stuff on my own. There was this YouTube video, and it was helpful because the guy had the webcam, and he was doing the right hand rule, and I could see what he was doing, so that was nice. And then resistance over length was a little weird to see, just kind of a busy step. If that was like a test question, that would be 3 points. Yeah, so that's kind of it. It's I feel like the whole challenge of this problem is kind of the figure eight stuff, and I guess understanding Lenz's law enough to kind of take this thing on. So thank you for watching.